Anyone? Or like no preference? So I did get an email. So like once you finish the quiz is automatically graded because it's like multiple choice. But like your scores are hidden until like everyone finishes. So yeah, okay. Let's get started. So what happened? Screen. Okay. This time my Apple Pencil's fully charged. So today we will go over subsequences. So let Sn be a sequence. A subsequence is a sequence. They write TK, but really it should be like, SNK. So where for each K, there is a positive integer nk such that n1 less than n2 less than nk less than nk. So I'll sort of explain what this part is. I wouldn't worry about it too much. So I'll sort of tell you why we need that, I guess, this part. But normally we write, like if Sn is our sequence, we write Snk for our subsequence. And then a subsequence of this, we just keep going. So we do like Sn sub k sub j, right? So that's like the usual notation. So like before I explain like the top part, why we need that part, like an example would be like for Sn is just the sequence, right? S2, S5, so on and so forth, right? S6. So a subsequence, I'll just make it up, right? An example would be S3, S5, and then everything else is the same, right? S7, S8, S9, so on and so forth, right? So here, this is S NK, where this is SN1, right? When K is 1. So remember, our index now is K. So this is for K equals 1, our first term. And so this is when N1 is 3, right? Because, if you match it, it's the third term. This is SN2, where N2 is what? N2 is 5. And this is SN3, where N3 is what? 6. SN4, where N4 is 7, so on and so forth, right? So this is like a subsequence. So the reason we have this top part is, so if I gave you a sequence with numbers, so like let's do this sequence. Sn is 1, 2, 3, 4. So you could sort of think of a subsequence as just like a subset if you view a sequence as just like a set of numbers, an infinite set of numbers. But it's ordered. So what I mean is you can have this. So can be, you can have 1, 3, 5, 6, 7, 8, right? So clearly like it's going in an order, but this cannot be a subsequence. You can't go 1 to 3 and then back to 2, and so on and so forth, right? Once you hit this term, you have to go to everything past it. You can't go back to the term before. So another thing that will be like 1, 5, 3, right? So once you reach 5, you can't go back to 3, right? So you see here, once I reach S3, if my first term is S3, I can't have S1, S2 anymore. So this is pretty much what this part is saying. It's like this this is like the ordering. So I wouldn't worry about too much. It's just basically saying like we can't have these scenarios. So like your terms be in an order. Okay. Any questions so far? Okay, so there's this theorem. I wouldn't really. I don't know if it's that important, but let Sn be a sequence. Then if t is an R, so t is a real number, then there is, what is happening? Is a subsequence Sn converging to T if and only if this set is infinite for all epsilon bigger than 0. Hopefully this is clear, right? Because if the set's finite, then you can't have a subsequence, right? If a subsequence converges, it better be like past some point, by your definition, past some point capital N, you are less than epsilon. But if there's only finitely many, it's impossible, right? You can't say past, because once you say past that point, it's infinitely many terms, right? So hopefully that is clear.
I have a question.
Sure.
You wrote n in natural numbers such that, and then what was it right next to it that you wrote?
Minus t.
That's s sub n minus t.
Less than epsilon. It's this.
Okay, gotcha. Thank you.
Okay. So next is if sequence. Yeah, I wouldn't worry much about this theorem. I don't think it's that important. is unbounded I don't know what's happening with my pencil. Unbounded above, it has subsequence. Please. Going to infinity with limit infinity. And similarly, if you are unbounded below, unbounded below, it has subsequence going with limit. Hopefully this is clear, right? If you're unbounded, so certainly you could be unbounded above and below, right? So like the limit cannot exist, but you like, for example, something like this, right? Like this, right? It's unbounded above and below, right? Because if you consider the odd terms and the even terms, the even terms go off to infinity and odd term goes off to negative infinity. So in this case, your subsequence for limit to infinity would be the even terms, like n equals 2k. And the odd terms n equals 2k plus 1 will give you limit negative infinity, right? So, okay. Now, here's the nice thing, which hopefully you should agree is true, or else, everything breaks loose. If Sn converges to S, so goes to S, every subsequence should as well also converges to S. Hopefully this is clear, right? Because if you think of the subsequence as that list, if the whole list went to S, a subset of that list will still go to S, right? So, okay. So this thing I won't go over, but you could read the proof of 11.4. I also don't think, so this is important. Yeah, this thing is very important. But I don't know, I feel the next part is also not very useful, but please, what's happening? Hold on, let me reset. There, why is this happening? There we go. Every sequence Sn has monotonic subsequence. Yeah, I wouldn't really worry about this part. This one's big though. So this one's like the big theorem. If you're gonna memorize something. Bolzano-Weierstrass theorem. So it says every bounded sequence has a convergent subsequence. Okay, so basically this is the idea. It's based on this fact. So example -1 to the n, it doesn't converge, right? But there's a subsequence that converges, right? So we know this thing does not exist. But we can certainly find a subsequence that does, right? Because here, right, this sequence is bounded. So this theorem says there's a convergent subsequence, and we can certainly find one, right? We take all the even terms. So if we take, but consider all even multiples of n equals 2k, right? So all even multiples, right? N equals 2k, k and z. Then we just get the sequence of ones, right? So this is an example of so this is my sequence SNK, right? Where N1 is 2, N2 is 4, N3 is 6, so on and so forth, right? And also you could pick out the odd ones, right? The odd ones. Okay, so here I can choose my sequence to be this, right? So in fact, this one actually has two convergence subsequences. At least with the same, I guess, two limits for convergence subsequences. So this is certainly n1 is 1, n2 is 3, n3 is 5, so on and so forth, right? Okay, any questions so far? Just making sure everyone's on page. Okay. So here, now this might be a bit confusing, so make sure you, so we define a subsequential limit is any real number. Now this is why I don't like it. Negative infinity or positive infinity. That is the limit of some subsequence Sn, right? It's exactly what you think, right? A subsequential limit. It's the limit of a subsequence. It has the word subsequent in it. So some subsequence of Sn. So this is why I don't really, you should make sure you memorize this, because normally when we say limit exists, it converges to a number, right? So when we say the limit goes to infinity, that means the limit doesn't exist. But here we say we allow negative infinity and infinity to be like a limit of a subsequence. So okay, so we let S be the set of all subsequential limits. So basically, this is what it means. All possible limits of all possible limits of subsequences. Right. So if I gave you Sn, consider any subsequence. If it converges to a limit, put it in the set, right? And it could be the subsequence doesn't converge to something. In that case, you don't put it in a set. But if your subsequence goes to infinity, positive infinity, or goes to a number, you put it in that set. So, and there is a theorem that says the supremum of this set is just the lim sup of Sn, and the infimum of this set is just the lim inf. Okay, so any questions so far? So this is pretty much all we have for subsequence. We'll start doing questions now, but okay. So 11.2, I'll do the first three. I'll let you think of the fourth one. In fact, I just talked about the first three. So here for part A, I need to give a monotone subsequence, right? For AN. So it's either has to be increasing or decreasing. So certainly for AN equals -1 to the N. I need to give a monotone subsequence. You just take N equals 2K, right? We went over this before. This is just a sequence of ones. All right, this is certainly, in fact, by definition, it's increasing and decreasing. Because remember, increasing is less than or equal to. So equal to, here, all our terms are equal to. So, and same for decreasing. Okay, so this sequence is monotone because it's constant. So now for each sequence, give its set of subsequential limits. So what are all the possible, limits this sequence can go to? So I'll let you check that it's, the only possible. So certainly we showed above that 1 is a limit, right? That this sequence converges to 1, right? And the odd ones, the sequence converges to -1. So you could show there's no other. I think it's pretty simple. I mean, your sequence only has two possible numbers in it. So, okay. Now C, we have that, what is C? Give its lim sup and lim inf. So here, right, I did this a few discussion sections ago, right? How to calculate lim sup, lim inf. In this case, you could use this part if you want it faster. The supremum of the set of subsequential limits and is just the lim sup, and the infimum is just the lim inf. So check only. So our set S is just -1, 1. So lim sup of -1 to the N, using that theorem, is just the sup of S. But supremum of this set is just 1. Lim inf of -1 to the N is just infimum of this set, and it's clearly that's -1. So yeah. Or you could just use definition, the definition of lim inf, lim sup to show this. It's not that bad. Okay, what should the sequence, okay, so does this sequence converge, right? So this sequence diverges, right? -1 to the N does not converge. Don't ask me why I went from like dot to like parentheses, okay? And the last question is it bounded? So this thing is bounded, right? Because the only terms are -1 and 1. So it's bounded by 1 and -1. So, okay, so Bn is now 1 over n. So part A, I need monotone subsequence, right? In this case, you could just take Bn itself. So certainly the whole sequence is a subsequence of itself, right? You just let nk be k. So here, and 1 over n is decreasing, right? So it's monotone. Now B, I need to find its set of subsequential limits, right? Now here is where we use that theorem. So that's why I said it's sort of big. So we had right here, I started right here. if a sequence converges, every subsequence has to also converge to that. So we know 1 over n converges. So it converges to 0, right? So every number, every subsequence has to also converge to 0. So the set S of subsequential limits is just 0, right? There's no, you know. And if you like in this case, you do either case, right? Lim sup n equals infinity, 1 over n. In this case, since limit exists, you can use that theorem that says, you know, limit is lim inf, which is lim sup if the limit exists and is 0, right? Or you just calculate sup s is 0, inf s is also 0, right? So either case. Now D, this sequence converges, right? And E, it's bounded, right? So it's bounded by, you know, 1 and 0, right? Bounded above by 1, bounded below by 0. So Cn is n squared. So let me go. Let's do one more. So here I need a monotone subsequence. Just take Cn itself, right? N squared is certainly increasing, right? For n positive, right? I mean, for n natural number. So for part B, I need the set of subsequential limits. So here, I'll let you check that S is just plus infinity. Yeah, no matter what subsequence you take, it's gonna go off to infinity, right? Because n squared just blows up. So, and clearly using that theorem, you get that lim sup n goes to infinity, n squared is and lim inf is also, yeah, I guess by definition, I guess I never really characterized what it meant to take supremum of, like, you know, but yeah, if S has positive infinity, that the supremum is infinite, yeah. So I know I never really defined that, but D, so this sequence diverges, right? It diverges to positive infinity. And E, it's unbounded, right? Okay. So I'll let you try to do Dn yourself. The monotone part, you have to figure out at some point it's going to be the 7n will, you know, the 7n will win. So you can just say some point it's going to be decreasing. Okay. So let me go to the harder questions, like the more theoretical ones, I feel. Yeah. Okay. So let me go over what enumeration of rationals are. So Qn, enumeration of rationals. So of rationals on 0, 1. Right? So here, this is, let me sort of define what enumeration is. So Qi is in Q, it's on 0, 1, right? Intersect 0, 1. 0, 1. For all I. So every term in your sequence is a rational number. And the second part is for all Q in Q intersect 0, 1. Q is Qi for some, Qj for some J in N. So the second part means every rational number, you know, everything in here is hit by our sequence. So our sequence covers all rationals on 0, 1. It misses none of it. And the only terms in it are just, you know, the terms in here. So an example, you know, I could show you, right? Like How do you get all rationals on 0, 1? Well, you consider denominator 1, denominator 2, denominator 3, right? Denominator 4, so on, so oh. There should be 4 terms for this. Right, so 1 over 1, 2, 1, 2, 3, 1, 2, 3, 4. Right, this is certainly an enumeration, right? So this is Q1, Q2, Q3. So Q4. Right, so you see here, this will cover all rationals on 0, 1, right? Because any rational is just of the form P over Q, right? And if it's on 0, 1, it's like P less than Q, less than or equal to Q. So here, this is, I guess, let me just write one possible enumeration. So it doesn't need to be this, right? It could be something else. There could be another way to organize these terms, but so let me just write, doesn't need to be of this form, right? Okay, any questions on what enumeration means? Is everyone clear on that? Because we can't do the question unless you understand what enumeration means. Okay, great. So the first part is A, give the set of subsequential limits for Qn. Yeah? So A, give set of subsequential limits for, it's Qn, right? Yeah, Qn. So basically saying take any subsequence of this, show what can it possibly converge to, right? And what you're going to see is rationals are sort of like they're dense, right? They're like, you know, given any real number, you could find a sequence of rationals going to it, right? So basically, I claim that the set is actually, so we are on, you know, we are on 0, 1. This is open, right? But we certainly can go to 0, right? So the rational is like 1 over n converges to 0, right? For example. So you can see that this converges to every real number in here is set of subsequential limits. Right, so let's prove this, right? So what do I need to do? So let S be in here, right? So it's some real number in 0, 1, right? And basically I need to find a subsequence. Oh, it's starting again. Subsequence for Qn that converges to S, right? So how are we going to do this? Well, I know that we play that same game. You remember how, like, for like the supremum, we sort of took like 1 over 2 to the n, and we consider intervals like a half, a fourth, 1/8, or anything that goes to 0. So that's sort of what we will do. So like consider, you know, S minus a half. It doesn't need to be a half. I'm just choosing, you know, I'm just using the fact 1 over 2 to the n goes to 0. Right, so here, this thing, so S minus a half plus, not plus, S plus a half intersect 0, 1 is some interval, right? That's all I care about. So by density of rational, there exists rational in here. So it's actually in here, but certainly if you're in here, if you're in the intersection, you're in 0, 1, right? There's a rational in 0, 1 such that I'll call it Q. There's this rational in 0, 1. Call it Qn1 such that Qn1, please, where Qn1 is in, you know, this interval, right? Is in so hopefully you see the next step, right? This will be like the first term of my subsequence. Now here's the tricky part. You want to say consider s minus a fourth now, s plus a fourth, right? So, and basically you want to say the same thing, right? You then s minus a fourth, s plus a fourth, intersect 0, 1 is again some interval. I don't care what it is. All I care about is that it's some interval. And then you want to say by density of rationals, there's some, you know, rational number in this thing, right? The only problem right now is it won't be a subsequence necessarily, right? So let's assume our Qn, right? It's Q1, QK, so on and so forth, right? This is our original sequence. Let's assume Qn1 was here, right? This is what I mean by the ordering part. So here, if you just repeated the same argument like the paragraph above, you get a rational in this interval, but the rational could be like right here, right? Right, could be the rational you chose could be like this could have been your Qn2, and that's no, right? Because again, a subsequence has to be ordered, right? You need your next term has to be past Qn1. It can't be before, right? So, but this problem can be fixed because what you basically say is there are only let me just write it like this. So I'll write like this. So this is some interval. So there are infinitely many rationals. Hopefully you proved that, right? An interval has infinitely many rationals. But if you consider all elements Q1 all the way to Qn1, this is only finitely many, right? And this interval has infinitely many rational numbers. So basically, and we know that from above, it's an enumeration, right? So you must hit every rational number in here, in this interval. And there's infinitely many, and there's only finitely many here. So there exists rational number past Qn1 in ordering. I write like this, in ordering such that call it Qn2 such that Qn2 is in. So yeah, this is just the extra argument you need. Everything else flows smoothly, right? And then same thing, right? You consider, you know, so you consider s minus 1/8, s minus s plus 1/8, and then same argument, right? Same argument. Only finitely many values from Q1 all the way to Qn2, right? And there's infinitely many in that interval, and then you get a Qn3. and then you keep going. Yeah, and then that'll be your subsequence. And it converges to S because you see your intervals converge to S, right? So if S is here, you first consider a half, right? This is length a half, and then length a fourth, length 1/8, length 1/16, and so on and so forth, right? The important part is this ordering property. You need this like the fact that an interval has infinitely many rationals to get a rational number past Qn1. So ordering is preserved. Okay. Any questions? So yeah, this problem's pretty hard. You have to think about it, but hopefully it's clear.
Can you scroll up a bit?
Oh, sure. So ... means like repeat argument. Yeah, I'll give you like a few seconds to digest this.
Okay, thank you.
Okay. Okay, does everyone understand why I made it a bit more complicated than it needs to be? Or because if you just ignored this argument and you just and you just keep repeating this part, density of rationals only give you a rational number, but it doesn't give it. The point is, it might give you something before Qn1, and you don't want that. So, okay, good. So let's continue. So let's do 11.7. Yeah. Rn enumeration of set Q of all rational numbers. So this one is a bit harder to imagine, right? Because the one I wrote is clear. It's an enumeration of rationals on the interval 0, 1. There's actually there is a sequence that enumerates all rational numbers. This one is a bit harder to imagine, but yeah, it is doable. So okay, so I need to show. So let's assume we have that. Show there exists a subsequence Rn k such that limit k goes to infinity, Rn k is positive infinity. Oh, sorry, I didn't do part B. So sorry, part B. I want what was it? Part B of I think I want lim sup and lim inf, right? Lim sup. But here, remember, lim sup was just sup of S, right? Where S was our set of subsequential limits. And lim, I don't know why my pencil's like this. Lim inf is just the infimum of this set, right? And we just showed above S was R intersect 0, which is basically just 0, 1, if you like. Yeah. So what is the supremum of 0, 1? It's 1, right? And infimum is 0, right? So that will answer part B. Okay, so let's move on to 11. Interesting. 11.7. So here we have that Rn, please work, Rn enumeration of set Q. And we want to show there exists Rnk such that Rnk goes to plus infinity. So this is rationals, yeah. So again, we're going to need that argument as before, right? The fact that an interval has infinitely many rationals to get a subsequence, right? So, but the idea is clear, right? How do you get a subsequence going off to plus infinity? Well, you consider you just truncate your intervals, right? You go from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and then you get a term on each one, right? So one possible way to do this is consider 1, 2 as Rn enumeration, right? Of all rationals. It must have all the rationals inside of 1, 2, right? So there exists Rn1 in Q such that Rn1 is in this interval. So the first term, no issue, right? So again, if you wanted to, this is the issue, right? So if you consider now, so hopefully you know what I'm going to do. I'm going to go 2, 3, 3, 4, 4, 5, 5, 6, and then this thing will clearly go off to infinity, right? Because I'm taking intervals that go off to infinity. So if you just said, so this is no, I'll write it like this, just to see, right? As Rn enumeration, there exists Rn2 in Q, such that Rn2 is in. So again, this is what I mean. You suffer the same issue as the previous problem. The point is, if this is your Rn, so what I do? If Rn was, R1, R2, R3, Rk. If Rn1 was this term, it could be your enumeration had Rn2 here, right? And that is a big issue because you won't have a subsequence anymore, right? So again, you argue the same thing, right? It's the same argument as before. So let me just write the right way. So there are infinitely many rationals in 2, 3, right? But the set R1 to Rn1, whatever Rn1 is finite. So there exists rational past Rn1 such that, so by past I mean in ordering, yeah. Call it Rn2 such that Rn2 is in 2, 3. Yeah, so that's sort of, you need this additional argument of like infinite to finite, right? And then so on and so forth, right? And then consider, what did I do? 2, 3, 3 to 4, get a same argument, get Rn3, right? And then, you consider n plus 1, same argument, get I don't want to write n again. Rk, k plus 1, get Rnk, right? So this sequence you get will certainly go to infinity, and it's a subsequence. So honestly, the hardest part is this part, getting an actual subsequence, not just any any list that goes to infinity. Yeah. Any questions on this? So hopefully this covers, I think these are like the hardest questions on this chapter. So yeah. Okay, any questions? So that's all I have for today. So if anyone knows what's happening with my pencil, please tell me. Because I mean, it's at 80% right now. So,
Excuse me?
Yeah?
Can you explain the last homework B?
Last homework B. What do you mean?
The last problem B. The like 10, 11 B.
Oh, you talking about homework. Where's I think this is just an opinion question, right? you just try out.
You do not have to provide exact the correct answer.
I don't think so. It's just your opinion.
Okay, thank you.
Why don't you just try out a few numbers? See where it goes to, I guess.
I have a question about the midterm.